Hello gentlemen, welcome to our section 6.6 video on factors in reaction rates. Now we're going to be studying what factors actually do affect the rate of reactions. Now first let's stop and talk about what reaction rate is. Reaction rate is defined as the decrease in the concentration of the reactants with a corresponding increase in the products over time. What that means is we're looking at how the concentration of your reactants decrease as your reactants turn into products, and the concentration of your products would increase. One is turning into the other over time. That is known as your reaction rate. Now, in our investigate, we looked at different factors in the laboratory. The first one, in experiment 1, was the concentration of your reactants. The second one was temperature. The third, surface area. And the fourth was catalyst. And this is the demonstration that I did with the decomposition of my peroxide. Hydrogen peroxide. Now, all on the molecular level, these factors above, 1 through 4, either increase or decrease the collision frequency of the particles of the material that we're talking about. And remember, collisions are when chemical reactions actually happen. So frequency, the rate at which collisions happen, will increase or decrease the rate of our reactions. What other factors can influence the rate of the reaction besides the 4 that we named up here? There are some down here. Particle size can influence the rate of the reaction, gas pressure can, agitation can, the nature of your solute and the solvent, just what they are in general can affect your rate of reaction. Now, let's look more closely at the 4 main ones that we've prescribed up there. The first one, is concentration. So as we look at the concentration, we're talking about the concentration of our reactants. The example that we had in laboratory was we used 1 molar hydrochloric acid versus 0.1 molar hydrochloric acid when they reacted with zinc metal. Now, an increase in concentration means an increase in the number of particles in the reaction. So we're talking about particles still. Different concentrations have different number of particles. We get that from this equation. If you remember, concentration is equal to the number of moles of your solute per volume of your solution. In our example in the laboratory, we had 2 solutions. They both had equal volumes. So the bottom of our equation here isn't changing. But they had different concentrations, meaning they had different number of moles per this volume. The 1 molar solution, the more concentrated solution, had more particles, more moles of particles to react with the zinc. This 0.1 molar solution had 10 times less particles to interact with the zinc. So, still particles there, but not nearly as many as the 1 molar. So an increase in your concentration means an increase in collision frequency. There are more particles here to interact with the zinc, thus more collisions. So your collision frequency goes up, and your reaction happens a lot faster with more particles present. The second factor that affects reaction rate is temperature. The example here from the laboratory was we used tea bags in hot water and tea bags in cold water. And you saw your observations there for yourself. The kinetic theory states that particles move faster at higher temperatures. We know that. And they move slower at lower temperatures. If you heat up particles, they move fast. In a cool environment, particles are moving more slowly. Here in red, the faster the motion, the higher the kinetic energy. Deals with motion, the energy of motion, which means an increased chance of particle collision. The more kinetic energy particles have, or the more movement particles have, the higher chances they have of actually colliding with each other. So increasing the temperature increases the chances of particle collision. Also, with the increase in temperature, we increase the chances of a particle having enough energy to equal that of the activation energy or to exceed that of the activation energy to actually make that reaction come to pass. Let's look at our third and fourth factors. The third one was surface area. We looked at this when we talked about, or when we, in the laboratory, went through putting the Alka-Seltzer tablets in water. Some were crushed Alka-Seltzer tablets, some were whole Alka-Seltzer tablets. Now, the crushed tablets had a greater surface area. Just think about the amount of space that's there. The crushed tablets had a greater surface area. More of those particles were exposed. Whereas in the whole tablet, the outer edge of the tablet was exposed to the surroundings, but the inside wasn't. Nothing could react with those particles inside that tablet because they were locked in by the particles around them. But by crushing it, you expose more of those particles to the environment around it. As a result, this allows more particles to interact more frequently with each other. The particles in the water can interact with the particles from the Alka-Seltzer tablet, especially when they were crushed. And that means more particle collisions, which means a faster chemical reaction rate. My last example, the catalyst. Now this was done in the teacher demo that I did before class. I put hydrogen peroxide in a graduated cylinder, and I put a catalyst in there to create a faster reaction rate. It was a decomposition of hydrogen peroxide. I'll get to the actual formula momentarily, but a catalyst is defined as a substance that speeds up a reaction without being permanently changed or consumed in that reaction. So a catalyst isn't used. It's like an instigator in a fight. So if two people are, wanting to react together, that instigator will egg them on and say, yeah, you said this about your mom, or whatever the case is. And the fight will happen, and the instigator is just going to walk away, and he doesn't get involved in the fight at all. The catalyst is that instigator. It's used in the reaction to lower the activation energy of that reaction, meaning making that reaction happen faster, but it is not used up itself. So when we think about this last point, lowering the activation energy of the reaction, we know when we look at our energy diagrams, we have our potential energy increase. The activation energy goes up, and hits the activation complex, and then it forms the products. What the catalyst does is it lowers that energy. Instead of going up to this point and then forming your products, the catalyst brings that point down here. So you don't have to go as far, and you can get to your products faster, meaning the reaction goes faster. An example. In class, we had hydrogen peroxide decomposing into water and oxygen gas. In order to symbolically write this, we don't put the catalyst in our equation where it could be balanced or confused as a reactant. It's not a reactant. It is not used in the reaction. So we put it above our yielding sign. Our catalyst for that particular demonstration was magnesium dioxide, which also we would know how to name as magnesium 1 oxide. All right, gentlemen, so take these 4 factors into consideration when thinking about reaction rates, and take good notes. Come to class prepared with questions tomorrow. Adios.